Hello guys. So this is Vignesh, and today I'm going to discuss about GraphQL, blockchain, and Web 3.0. So three different topics, three big domains to discuss, and I'm pretty sure it's going to be interesting, especially because of the relation between all three. So yeah. So to get started, just let me start with an introduction about myself. So I am Vignesh, as he introduced. So I call myself a generalist. That's how I like to introduce myself. I work with the guild as a software developer, which makes open source GraphQL developer tools and provides consultancy to other companies. And I am a founder of a startup called Time Campus. I'm still working on it, and I'm the CTO of Convent.ai, which is again a Singapore-based startup which is working on conversation intelligence. So this is my profile. This is why I said I like to call myself a generalist. I am a product consultant at Shipper. So just to give you a intro on the org I work at. So this is what the guild ecosystem looks like. So if you are using GraphQL, by any chance, you would have come across one tool or the other from the guild ecosystem. So yeah, it's a pretty tightly coupled ecosystem. At the same time, it allows you to use any one of the tools from the services which they provide. So you might have used any one of these tools if you are working with GraphQL and Node.js and TypeScript, most probably. And this is what we are doing at Convent. So we are actually building, a recruiter bot for everyone, for candidates. So for to attend assessments better, to attend intelligent assessments better. That's what I'm doing. Just to give a quick intro on what I'm doing behind the scenes. And yeah, before we jump onto the talk, like today's talk is going to be about blockchain and other parts of GraphQL. If you want to go deep into GraphQL, I have two other talks which you can actually go to YouTube and you can find them. Yeah, let's quickly get onto the topic now. So when we are talking about Web 3.0, the reason for the Web 3.0 to evolve, has been manifold. So we started with the PC era, then we came to Web 1.0, which was typically called a read-only web, and then we came to Web 2.0, which is where we are in right now. So where we have social media, interactive content, rich text, and things like that. We add more interactivity in Web 2.0. That's where we came in Web 2.0. And then now comes Web 3.0. Now the future of web, which is typically called Web 3.0, is where we are headed. In fact, it's already there. So just to give you an insight on what the difference is between Web 1.0, 2.0, and 3.0. So as I told you, 1.0 was read only, 2.0 was information interactive, and 3.0, it's more decentralized, private, and secure. We will come to see why we moved to Web 3.0. But before we do that, if you're using any one of these apps, Facebook, LinkedIn, Twitter, Instagram, Google, YouTube, anything for that matter, this means that you are using Web 2.0. The reason being, so there is an entity which is basically controlling your data. There is an entity which is actually helping you complete transactions, and this is a centralized entity we are talking about. So if you are talking with Facebook, if you are transacting with Facebook, if you are sending a friend request in Facebook, you're talking with Facebook. So if Facebook is down, then you pretty much cannot do anything in Facebook. So and Facebook holds control of your data. So that's how it is right now. So for instance, this is how a Web 2.0 architecture looks like. So if you are using any one of these apps which I just showed you, so this is what the architecture looks like. You have the browser which the user is accessing. You have a front end layer, which is what is being rendered on the screen, which is typically in JavaScript, HTML, and CSS. Then we have a backend layer, so which can be in any one of the languages: Node.js, Python, Java, Golang, Rust, whatever you call it. And then we have a database layer. So we call it as a three-tier architecture, right? So we have front end, back end, and database. So that's what we have in a typical Web 2.0 application. And this has been working very well for quite a long time now. But as the web evolves more and more, the threads also evolve more and more. The needs also evolve more and more. So the best way to find, the best reason for new innovation is a problem, right? So that's where Web 3.0 also came into picture. So Web 2.0 had problems, and that's where Web 3.0 had to come in to solve those problems. So, like, if we want to look at what the problems are of Web 2.0 before we even jump to Web 3.0, so one thing is it was a single easy target for hackers to come in, take your data, do anything with your data, and basically we were trusting all our data with a single entity, and we assume that nothing will go wrong with the data, which we have been proved wrong for quite some time. We saw Equifax, we saw Facebook data breach, and we saw a lot of data breaches in the past, Visa data breach. So all of these are problems of entrusting your data in a single entity, and that's the problem with Web 2.0. And also, you assume that your data is not being sniffed, your data is private. That these are all the assumptions we make, but in reality that's not the true picture, because you are ultimately putting all your data in a single place, which is something like a single point of failure. So if your data is lost, it's lost. So if so your data can be modified by the party whom you are entrusting to as well, without your knowledge. So things like this can happen, and there is no way to for you to enforce any rules, enforce any what do you say, framework to control this. There is no openness, there is no transparency, and sometimes your data can be mishandled in any number of ways. So this is the challenge we saw in Web 2.0. But at the same time, it is not without its own advantages. It comes with advantages as well. Now let's come to Web 3.0. Before I go to Web 3.0, the reason I am talking about Web 3.0 today is, so when we are talking about GraphQL and the future, so that's where GraphQL plays a major role in putting together Web 3.0. We will see why. So when you see Web 3.0, it involves a lot of components or modules within. So one is, the web has to be semantic, which means that it has to contain meaning. It should not be just about text. It should not be just about keywords and values, but it should be graph of data. So that's what we call, right? So we have data which is connected, and connected data conveys more meaning. So we have a connected data, we have intelligence in data, and we have ubiquity, which means that it should be accessible. Data should be accessible anywhere. Then we have enhanced connectivity. We have a peer-to-peer network. Now peer-to-peer network is what we will be concentrating on today predominantly. We have 3D graphics. So all of these are other portions of Web 3.0. So Web 3.0 doesn't just include a decentralized network. So if you saw the challenges before in the previous slide, the major challenges were because the data was entrusted to a single entity. So if we were to avoid issues or problems with our data caused because of entrusting our data to a single entity, then the best way to handle that is to actually take the data, split it into multiple pieces, or distribute the data as we call it, and make sure that there is a signature or trust certificate for your data, so that we know that it is not tampered with. So we also have a clear audit trail on where the data goes and things like that. At the same time, maintaining our privacy. So if we want to have all of these in place, that's where Web 3.0 actually comes into picture. So now, when we talk about Web 3.0 and Web 2.0, so rather than just putting in the terms, so let's have a look at all the apps between 2.0 and 3.0. So when you're talking about 2.0 and 3.0, so browser we have Chrome in 2.0, 3.0 we have Brave. So Brave, there is something called as basic attention token, or BAT as we call it. So people are paid for viewing content. Creators are paid for viewing content without having to track your activity. At the same time, we have storage, Dropbox and Google Drive 2.0, which is centralizing your data all in one place to a single entity. So if you're putting your data in Google Drive or Dropbox, you're basically entrusting your data to them. So, but you have IPFS, which is distributed, and it is pieced to multiple people. So, and you are signing them. So IPFS is interplanetary file system which is distributed across the globe. So like this, you have parallel technologies between Web 2.0 and 3.0. So you have Facebook and Twitter, we have Steemit and Akasha. So this is how the ecosystem currently looks like. So this is the transition we are making to the future. It has its own challenges as well. We will talk about the challenges of Web 3.0 in the future. But when we are talking about the apps like these, so we call it dApps, or rather decentralized applications, because it is distributed and not centralized. So that's the reason we call it as dApps, while we call Web 2.0 as apps. So this is how a typical Web 3.0 application looks like. We have cut all the complex parts. It's just talking about the most important parts of Web 3.0. We will come to the complete architecture diagram in just some time. At the end, if I find time, I will show you a demo as well. So let's see. A person is again accessing the browser, again looking at the front end. So the same thing applies here. But in the back end, if you see, you have an Ethereum virtual machine which is going to basically help you take the smart contracts which you have actually written in blockchain. Or rather, before we come to even Ethereum virtual machine, so what we have in the backend is a blockchain network. So blockchain network is where we are not we call it blockchain network, where we are not we are not centralizing all the things in one place. We are rather decentralizing all the things we do into multiple pieces. We are basically making the data immutable. So we will quickly look at what blockchain is, and then probably we'll come to this again. So yeah, this is what blockchain looks like. So it is programmable. So a blockchain is a programmable technology, which means that you have smart contracts. So smart contract is something where you have logic. So let's say that I have $1,000 and I give $1,000 to someone, a person who is going to basically rent me his house. So I am going to pay $1,000 and he's going to rent me his house. If that's the case, that's the contract I have with the person. So so in this case, in case of blockchain, it's something similar. So we are basically having multiple states and a contract which is nothing but logic, which will help you change from state A to state B. So if you want to change state A to state B, you have to execute a logic. And similarly, you have blockchain networks are secured because you don't actually lose anything. I mean, everything is encrypted, everything is hashed, so and everything is signed as well. So even if something is tampered, you can always verify the signature. It's anonymous because you can't actually understand who put the block in the blockchain. It's completely private unless you actually make it public. It is possible to make it public, but by default it's private. And then it is distributed by nature, so you don't centralize all the things in one place, but rather all the data you put, all the logic you have, everything is distributed across multiple people, and it's immutable. So which means that the data you put in already cannot be modified directly. Rather, you are actually going to have to create new copy. It's something like a ledger, like an account ledger, where you create another copy of data with the updated value. So this is what we call a state change, right? And it is timestamped, so we can clearly monitor when the block came into the blockchain, when the and what happened at what time it happened. So all of this can be clearly understood in blockchain. So this is what blockchain network looks like. So I understand this is a GraphQL meetup. We will talk about GraphQL soon, but just to give you a background of how things work, I will just quickly have a look. So now that we talked about blockchain, Ethereum is a type of a blockchain platform. It's a sort of a framework where you have smart contracts in place, which is going to have logic to basically change the value from state A to state B, and that's smart contract as we mentioned. And we have blocks of data, and blocks of signed data, and we have Ethereum virtual machine, and its job is to basically execute the smart contract, convert execute the smart. I first of all convert the smart contract to bytecode, execute it, and then once executed, the final data has to be returned to the blockchain. That's the job of Ethereum virtual machine. So Ethereum is one of the type of blockchain networks. There are others as well. So I hope you got a gist of it. So this is how the process looks like in blockchain. So a transaction is requested and authenticated. So first of all, you start with the transaction you initialize the transaction first, and then a block is created with it for the transaction. And if you create a transaction, the same data, the data is sent to every node in the respective blockchain network. So for instance, if you create a block in Ethereum mainnet, the same block information is or metadata is published to all the blocks in the Ethereum mainnet blockchain. And we have the nodes which validate the transaction, which says whether this is the right transaction or not. You have proof of work, the block is added to the blockchain. So the reward is given because for people to participate in blockchain and for people to actually do work to verify the data we have in blockchain, we need some kind of incentive. That's why we have a reward as well. And then the update is distributed across the network. Since it's a distributed system, the entire network needs to know about the rest of the network. I mean, every node in the network needs to know about the rest of the network for it to understand where a specific data lies or what happened to the state, and to also come to a quorum on what the final value of the data is. And then finally the transaction is complete. So I know I'm going a bit fast because we have to jump into the important parts. So now you may ask, what about cryptocurrencies? So I am not talking about cryptocurrencies in today's meetup, but yeah, we have a lot of cryptocurrencies based on blockchain. So cryptocurrency is like an implementation, blockchain is like a protocol. So we have Bitcoin, we have Ether. Ethereum is a network, and Ether is the currency. And we have Solana, we have Dogecoin and other cryptocurrencies which are built on top of the blockchain protocol. So we are not talking about cryptocurrencies here. So, and when you're talking about blockchain, there are multiple different types of blockchain networks or multiple implementations of blockchain. So we have Hyperledger, Coda, Quorum, and again, I'm not touching this here because this is not a blockchain meetup. But overall, I would recommend Hyperledger, especially because Hyperledger is hosted by the Linux Foundation, so it has more backing, more community following than other blockchain networks. It has more maintenance than other networks. While all of these three are private, it supports private, it supports public, it supports high performance. So it supports all of these. The feature set in all these three are almost the same, but the backing is different. So that's why I would ask you to go for Hyperledger if you are going for something else. So, and just to give you an insight on how a contract looks like, so this is Solidity is the language in Ethereum, which is where which is what is used to write smart contracts. So this is how a smart contract looks like. So in Solidity, so this ultimately cannot be processed by Ethereum. Ethereum has to convert the smart contract to bytecode so that it can process that and insert it into the blockchain network. So ultimately, the smart contract is converted to bytecode. Smart contract is nothing but the logic to help you move from state A to state B. And this is how you write smart contracts. And when you're talking about blockchain transactions, so you have all of these contract code, transactions, previous hash, data hash. So this is how the complete verification flow goes. Like initially a block is published, then all the verification happens, everyone in the quorum agrees that this is the right transaction, and things like that happen in a blockchain network. So this is pretty complex to actually look at from the outside. So that's why we came to a decision, okay, enough is enough. So that's when we thought, okay, we need to have a better way to do all of this. We need to have a better way to make this easier for the client side applications to consume. So we cannot have this kind of complex complexity in the backend and have the client side or the browser consume this kind of blockchain, right? The problem is we are not just adding complexity to the backend, but also adding complexity to the front end, because we need to consume all these events in the blockchain for us to render in the front end. So that's where the graph came in. What the graph said is, okay, we will handle all of the things with respect to the front end of the blockchain, which means, so graph is nothing but just imagine graph like a graph like Google. So Google basically indexes websites and basically presents the search results for you behind the scenes. So ultimately it crawls all the websites, it indexes all the websites, and ultimately basically provide you the search results whenever you search for it. Similarly, you have the graph, which is indexing the data in blockchain network. It is indexing all the blockchain networks, and ultimately presenting you different subgraphs. So what you can do is you can query the graph for data like you query Google for search terms. So it's like a single point of contact for querying all the data from your blockchain. So you don't have to go and monitor the events. You don't have to update the contract regularly, but rather you can index the blockchain network you have using the graph. And once you index it, you can actually start querying all that you want using the API which graph provides. And the front end for the graph is GraphQL. So then now this is where GraphQL comes into picture. So now to give a pause and discuss about all the things we discussed till now. So ultimately, we have a Web 3.0 app which has a distributed backend, which is based on blockchain. I mean, Ethereum is a type of blockchain network. So we have an Ethereum-based blockchain network behind the scenes, which is ADAP. And so these Ethereum, blockchain networks are regularly emitting events on what happened in the network. Like as soon as any change happens, it emits events. So that's what you see here as events. So all of these events are captured by the graph or indexed by the graph, and you can query those events indirectly. So ultimately, this is how the final architecture looks like. So you have this is quite complex, I know, but if you are venturing into the world of Web 3.0 at present, in fact, this is the biggest limitation of Web 3.0, to be honest. So I might not be a very big advocate of Web 3.0. At the same time, I'm not opposing Web 3.0 as well. The problem with Web 3.0 is it is complex for beginners to start with. So that's the biggest problem with Web 3.0, as people are trying to make it easy, but still you have to put together all these tools to have proper end-to-end Web 3.0 application. So you see a tool called MetaMask, which is used for authenticating, or it's like a gateway into it's like a great gateway into blockchain. So you have basically something which authenticates or signs the data which you have, signs you as a user. So MetaMask is gateway service to blockchain. So you have IPFS, which is the interplanetary file system, which is distributed file system across the globe. We have Infura, Alchemy, MetaMask. All of these are basically blockchain providers. The reason we need providers is because either we have to host the blockchain network ourselves, or we have to use third party providers. If we are hosting, let's say, an Ethereum node ourselves, it will be not feasible, because every time you have an Ethereum node in place, you are not just having your data, but you're also having the data from all the blocks in the entire global Ethereum network. So it will take days for you to, pull all the data. It will take huge compute power, bandwidth, and everything to host it all in your laptops. There are third-party services available to do that for you, because every block, as I told you, holds a copy of the entire Ethereum network. And we have Ethereum virtual machine smart contracts blocks, as we mentioned, so which forms the back end of the blockchain. And we have Polygon. We will talk about Polygon in a bit, but we have Graph here. Now the Graph's job is to basically make it easy for the front end to query the backend. So ultimately, GraphQL is where this is where the GraphQL part comes into play. Where GraphQL is going to be used as a query language to query all the data from this Ethereum virtual machine without exposing the complexity of blockchain to the front end. So that's how it works. And Polygon is used because Ethereum virtual machine, I mean, in Ethereum network, when if you are doing any transaction, it is actually paid, and it takes long time to fulfill or reach finality. So what people do is typically have a parallel blockchain network which does computation parallelly, and then finally aggregates the computer data and inserts the computer data onto the main blockchain. So it's like a parallel existence to blockchain where you do all the stuff temporarily. Just assume it like a rough notebook where you take down all the rough notes, and then finally when you know what you have is right, then you shift to the Ethereum network. That's so that is more faster than doing it directly in Ethereum network, and it has other advantages as well. So this is how complex the blockchain app looks like. And as you might know, I don't need to explain this because you are in a GraphQL meetup, but this is the one which you see in the left is REST, and the one which you see in the right is the GraphQL API. So you have one endpoint to query and multiple sources of data which you can query. So again, this is how GraphQL looks like. Now talking about the subgraphs, this is what the Graph Explorer provides. So this is how the different blockchain networks are hosted in the graph. For instance, these are all different contracts or different networks, all of which have their own GraphQL endpoint. So you can basically query the events on the graph, and you will get the data out of it. We will quickly see that now. How much time do I have? Okay. So let me quickly take you through a quick demo so that I'm just skipping this. And by the way, just to give you an insight, GRT is the graph token, which is like which is like a currency or metric used to identify the value in the blockchain network. So GRT is made by the graph. So I don't want to go through this now because we are short on time. And yeah, I'll quickly show you the demo just to give you an insight. Probably, if we find time after that, we can discuss more. So this is a network which I created already, and let me quickly open up the project which I created. So ultimately, this is how a subgraph definition looks like. So you basically mention all the configuration for the subgraph, and you basically mention the mapping parameters. So let me quickly take a new project, and I'll just do it for you. So um, probably it will take me 5 minutes. So let's quickly do the demo, and so that you will get an idea on how it works. So the first step to starting a blockchain is you need to, I mean, first step to publishing to the subgraph in the Graph Studio is basically to make sure that you have the tools installed. So first step is to install Graph CLI. So I'm getting the Graph CLI installed. So I already have it, I guess. So I have the Graph CLI installed. And the next step is to actually initialize my subgraph. So for this, what I do is, so I go to the graph.com. So if I go to the graph.com, what I can actually do is I have to log in. So I can log in through MetaMask. So there is something called as Explore Subgraphs. So I just click on that. So let me, right now I'm already logged in. So if you are not logged in, you have to use MetaMask to log in. So probably you can Google it and you'll find a way to log in. So I have to click on create subgraph. So these are all the different subgraphs which are already available in the graph. So now I am putting my subgraph in the Ethereum network. So that's why I select Ethereum mainnet. I set the name of my subgraph to be um, Zora test. I say continue. So a new subgraph is created for me, and I get a deploy key. So basically, what I am doing, going to do is, this is an NFT marketplace where there are multiple media galleries or multiple media being hosted. And if you see, each and every media has its own contract address, token ID, the blockchain network, and other metadata. What going to try do is basically query data from Zora using using the subgraph studio in the graph, using GraphQL basically. Ultimately, this is a blockchain network already, so I am going to query all this blockchain data using GraphQL. That's what I am trying to do. So let me quickly do that. So I go to okay. First step which I need to do is, so I have the commands in place. I'm just copy pasting it just so that I save time. So the first thing is I need to change the name of my network. So here in this case, the name which I created is Zora test. So I need to replace Zora test and subgraph studio from contract. So I will just explain what this command does. So we are initializing a new project. We are setting the name of the contract as token, and we are specifying the name of the subgraph which we have in subgraph studio. We are indexing all the events so that whenever so ultimately we are trying to generate code from the contract. So if we do this, what it's going to do is it's going to ask you what protocol do you want to use. Do you want to use Ethereum or do you want to use Near? So I say Ethereum, and it already has the name of the subgraph because we already specified it. I say Zora test. So Zora test. I want to create the blockchain in mainnet. So I select mainnet. So there are multiple types of networks in Ethereum. So there is mainnet and there is others as well. So you can have a look at it later. So contract address, so true. Okay. So I need to specify a contract address. So right now, if you see Zora.co, this is what I told I am trying to query, right, through GraphQL. So here I have my contract address. So I just go take that, I paste it here. Okay, it got my ABI application binary interface. So probably for some other day. So now it's going to create the project for me, initialize all the dependencies, scaffold everything. So ultimately, I need not do anything apart from just waiting for some time. Am I over time? No, when I started. Okay. So what I'm quickly going to do is, so I already have a project generated now. So what I need to do is, if you see this schema generated, you have all this schema. This is a GraphQL schema which you see here, which is going to be used for querying the respective blockchain network. I am going to replace this schema with my own schema, whatever I need. So I have a token type, I have a user type. So what I'm trying to do is I'm creating two types. These are custom types created by me. I'm specifying, okay, these are the fields I want. These are the data types, like you specify GraphQL schema. So I mentioned these are the two types I need. And then I go to subgraph.yaml, which is going to be the configuration for my entire subgraph. So if I have to specify any changes to my subgraph, this is where I specify that. So I basically go ahead and specify the start block ID. So this is something which you can get from Etherscan. So I don't have time to explain this right now, but if you go to Etherscan, you will be able to find the start block ID for this respective contract. So there is a website called etherscan.io. You can basically explore all the blockchain networks here. So yeah, that's where I get this start block ID from. So now ultimately I don't need all of these functions. These are functions which will get executed when the respective event actually happens. So I'm getting rid of things which I don't want. I just need just two events. So I'm just taking that all that alone into picture. I'm getting rid of all the things I don't want. Now the next thing is again I have the code already in place, so I'm just replacing the code for the sake of time. So we have all of these. So now that I have the schema in place, I need to basically generate the code. So first thing which I need to do is I need to generate the types for the respective schema from the code. So I run graph code gen and sorry. Okay, I'm in the wrong directory. So I go to Zora test. I run graph code. Then now what this is going to do is it is going to look at my GraphQL types. It is going to look at my configuration and it's going to generate all the things for me in generated folder. You see token.ts and schema.ts which is generated, which will basically query the network, query the blockchain network and give me the data. So ultimately it's generating me all the helper functions I need to basically query the network when I do the code gen. So now what I do is ultimately, so the final piece is this, where we actually specify what we want to do. So if there is no token, we create a token and we assign a contract and we basically save the respective token. If there is token, we return it. Similarly, if there is no user, we create a user and then save it. So ultimately, there is token and user. So you will get a clear idea when we actually do it. So now the next step to do is, so I need to authenticate first with the studio. So I guess I am over time. So what I will do is I will go to the existing network which I have, and I will quickly show you how the query works, so that I don't take the next speaker's time. So this is a network which I have already created. Ultimately, when you deploy this network in the blockchain, this is how it looks like. So you have the query, you have the different data types. So ultimately, if I just query the first five tokens, so I get all the content in the respective blockchain network. So ultimately, what I did so far is I created. I have an existing blockchain network which is Zora. First step. Now what I did was I used the same contract ID. I created my own subgraph. I deployed the subgraph onto the subgraph studio in the graph, and ultimately I am using GraphQL queries to basically query on the data on top of the subgraph. So I know for beginners this will be confusing, probably in a 30-minute meetup, so this might be too much for you to take in, but this might probably give you an initial start on how all of this works. So ultimately we are able to query the blockchain network for data, and this is how the data looks like. So if you want to go and look at the data, you can just go to the data and you will be able to see the data here, ours truly. So thank you. Yeah, you can actually see this demo here. I have pushed all the code, all the source code here, so you can have a look at the demo. So that's all I have for today. Yeah, probably any questions you have, we can probably catch up offline since I went over time. Thank you.
Okay, thanks, Vignesh. So let's see if we have any questions. Okay, so we have one. I've seen some confusion between Web 3.0 from 2001, semantic web, and Web 3 from 2021, which is the token-based decentralized web.
So yeah, semantic web is one part of Web 3.0 definitely, but that's just one piece which makes up the entire puzzle. Semantic web is definitely that, but the Web 3.0 is also supposed to be decentralized. It's just one of the characteristics, I would say. So
Okay, thanks. Do we have anyone else? Okay, looks like that's it. So thank you very much, Vignesh.
Thank you.